Now, somebody was asking me that since the Newton's method is very accurate, close to the optima, is there any other way? And the Newton's method is expensive because you need to compute the second order Hessian matrix and you have to take inverse. Turns out that you can compute these Hessian matrix inverse in a nice way using only the first order information, but obviously it's an approximation. So these methods are called quasi-Newton methods. So it's not Newton, but it's kind of approximating the Newton's method with a much less computational effort. Okay? So the way it works is you will be approximating the Hessian at the optimum, okay, starting from an identity matrix. So Hessian matrix is a matrix of n by n matrix. So you start with the identity matrix, and this identity matrix gets transformed with iterations. Eventually that matrix takes a form of the Hessian at the x star. Okay? Actually it does the Hessian inverse of the x star, so automatically does the inverse. So now you see that this is really a lot of achievement that people have done very early on, and there are not one but many ways of doing this. DFP is one method, BFGS is another method. These are the first letter of the last name of authors who have done this, so Davidson, Fletcher and Powell, and these are some other people who have come up with this idea. If you look at the proof of how they get this is very long, and there are some assumptions, but you can understand if you look at the original work. But for our purposes, we just need to know how they look like, what is the formula, and this whole philosophy of what's happening in this quasi-Newton method. Fortunately, both DFP and BFGS methods have a proof of convergence for quadratic problems. So if you have a quadratic objective function, these methods have a proof that it will eventually get to the optima. But for any other functions, there is no proof. Okay, the way it works is that every iteration k, you have a search direction again to go. So this is a line search you are doing. Most methods are like that, point by point methods. It's just that how are you defining the search direction? That gets changed from one algorithm to the other. We've looked at the steepest descent, where you always go along the negative of the gradient. When you looked at the Newtons, it's a bit more complex, but there is a search direction. But the rest of the algorithm is the same. Okay? Now here is the same thing. There is a search direction defined this way. There is a matrix AK multiplied by the vector del f, which is the gradient of f at the point xk. So steepest descent would have been AK is identity matrix, right? That would be steepest descent. But here it's AK. But you remember what was the Newton's method? Newton's method, the AK was the inverse of h. Inverse of h. So when I'm starting with I'm actually doing steepest descent. When I'm ending up with inverse of h, I'm actually doing Newton's. You've seen that in Marquardt's methods as well. But someone pointed out that Marquardt's method, you probably pointed out, still you have the computation of the Hessian matrix. Here, you are approximating the Hessian matrix, but you are not computing all the second order derivatives. These are all manipulations of a vector, so they are very, very quick. And I'll show you how the manipulation happens. So here is the Davidson, Fletcher and Powell method. You start when k equal to 0, that means you're starting, it's the steepest descent, which is the identity matrix. Then every iteration you change the a0 to a1 by this formula. So you have a0 over here, which is the identity, plus there are two terms that are added. It's very complex looking, but once you look at it, there is a lot of symmetry in it. Okay. Now what is delta x? Delta x is, so you started with x0, and then you got a search direction that says s0 is equal to a0 over the gradient at x0. So a0 is identity, so that means this is as if not there, and then you have negative of the gradient. So you are basically doing a search along the negative of the gradient at the current point x0, and you get a point x1, right? That will be the best point, x1 along that line. That's your x1 here, and x0 is the original initial point. So the difference in these two vectors is del x0. Okay? And then del e is the difference in the function value. E is actually the derivative. E is the derivative of xk. So this is the derivative at xk and derivative at x0. So you know x0, so you know the derivative vector. You just compute at xk, x1, so you know what is the derivative at that point. So difference in the derivative vector is delta e. So you substitute all these delta e's and delta x over here, you get the modified a1. and then you substitute the A1 over here, okay, at the point x1, and then you have a new direction. And that's no more steepest descent, because now A1 is not an identity matrix, it's been modified. So from after first iteration, it is no more steepest descent. It's moving towards Newton, okay? And then you get a direction, you do a line search, you find x2. At the x2, you find del x1 and del E x1, and substitute it here, and you get A2. So like that, you continue. It so happens that if you follow the structure of these modifications, because this is a positive definite matrix, the identity matrix is always positive definite, and the way these are computed from vectors, okay, they are also positive definite. So what you end up getting is always a positive definite matrix, and so you are guaranteed to improve your function value every iteration, which is not so in case of Newton's method. So in some sense, it is better than Newton's method, although it's approximating the Newton search. Okay, so the details, of course, you need to look into some advanced textbooks or the original paper if you want to know how this formula has come about. Then there is BFGS update. You see they have very similar kind of structure, but it's slightly different than that. But this also does the proof that for quadratic problem, it gives you the optima. So what happens in this problem, which is not quadratic, that I've tried, so started with x0 again, go like that, and then the steepest descent would have get it very quickly here, but this method takes a little round and comes back. Optimum is here, so if you do few more iterations, you are going to get there. But had this been quadratic, we would have gotten this in 2 iterations in the optimum. Okay, so the calculations are a little involved, but once you write a code, everything is calculated. It's a very systematic procedure. Most of the optimization algorithms with classical methods use this Davidon-Fletcher-Powell method, DFP method. They would say that we have used DFP method. If you read some optimization papers, they would say we have used DFP method or BFGS method. So now you know that how what are these methods, what are they talking about when you hear the word DFP or BFGS, right? These are quasi-Newton method. Again, to summarize, quasi-Newton's methods behave like a Newton's method at the end, but without having to compute the expensive Hessian matrix. So all the manipulations you do here is with vectors, okay, not with matrices. Is that clear? The overall idea? Of course, I didn't give you the details, but the idea is important here. Okay, so these are some unconstrained optimization methods that we looked at yesterday and up till now, where there was no constraint. First, we looked at single variable, because those are very easy to understand. And remember what we did in single variable? If you have to use a numerical method, there are 2 steps. First is to bracket, and then confine your search within that 2 bounds using golden section or interval halving, or there are some gradient methods we also looked at, Newton-Raphson, bisection, secant method. Then there is another class of algorithms for single variable, was this approximate methods, Powell's method that we talked about. You could do a quadratic approximation, so you need to compute only 3 points, compute the function values, and then you can approximate a quadratic function. And then optima of the quadratic function is assumed to be the next point, and then you keep doing this in an iterative manner. Then we move to multivariable, where we are using line search as a backbone of the algorithm, but every line search is a single variable optimization. So you see how things are nested. When you are doing multivariable, you need to call a single variable optimization. So you need to understand single variable optimization. So then we come to multivariable. The only thing is, when you start with a point, somebody has to tell you what direction you should go for do the line search. And every algorithm has a different way of computing. Now that's where you can come and design an algorithm as well. So at MSU, I teach a course on optimization where every student has to come up with a new method. Okay, not steepest descent, not Newton's, not anything, but you have to come up with your own method. You can use gradient, you can use any other. There are infinite ways of doing it, right? And then I give them some test problems, and they will try their method, and then they will compare against each other. Okay, so there is a deadline they have where they have to write a little report, and everybody upload their results so others can look at. Now, if you have submitted something, another student has to find out at least one from the other all others that have submitted and compare his method with the other person's method. So that way you actually learn how, but you need more time for that. I mean, you need to develop the method, you need to code it and run it. We can't do it in 2 weeks time, but if it's a semester long course, then we can have all those experiments. So that's really the way to learn, okay? But hopefully you are getting the idea of how these algorithms work. Now let's move to the most complex type of optimization problems is constraint, when constraints are there, okay? So far we didn't talk about them, okay? So first let's get the idea of what happens when you have constraints. So now my problem would look like this. Minimize the function fx subject to there could be inequality constraints or equality constraints and variable bounds. We looked at that before. And we also talked about what if they're less than equal to, you can multiply it by -1 and convert everything. So in this part of the lecture, we're going to keep greater than equal to as a default, okay? But some books consider less than equal to as default. So you cannot just simply take my notes and compare with that book because things are going to be a little different. So you need to first see what is the assumption of the problem, and then all the theories that's done from it is relevant to that formulation. Okay, let me define few things first. Active constraints are active constraints are defined at a particular point. So if you're talking about the optima, or if you're talking about any intermediate points in your algorithm, you may want to say, okay, these out of all these constraints, these few constraints are active. That means that solution X makes the inequality constraint with the equality sign. So inequality constraint says the G can be equal to 0, or it can be strictly greater than 0. Any of them is going to make it feasible. Okay? So if at a point X, any G is equal to 0, that means the point falls on the constraint boundary, then it's called an active constraint at that point. Some constraints may not be, the left hand side may not be equal to 0. It may be positive, okay, or 100.5. So then it still satisfies the constraints, but it's no more active, it's called inactive. So that means if you don't have that constraint, it doesn't matter, still this is a feasible solution. I mean, still you get the same result. If at the optima, some of the constraints are not active, that means those constraints are not important. So you laid out 10 different constraints to solve the problem. You went ahead and found the optima, and you figured out of 10, 3 of them are inactive. That means you could have eliminated those 3 constraints and still gotten the same optimum answer. So those constraints are unimportant. Then it's a very good information. See, I talked about knowledge, right? So when you see that, originally you thought all the 10 constraints are important, but now your result says no, these 3 are not important. So then you figure out what are these constraints, why are they not important, have I done anything wrong? Looks like they should be an important constraints, but it turns out to be not so. So if that's the case, then you can use, you can be a little relaxed for that constraint. If you're using very expensive material that involves that constraints, or let's say that constraints is the volume inside the can that I was talking about. And it so happens that that constraint is not that important, but stability of the can is more important for the optima. So now you can say, oh, then I can be a little adventurous here and increase the volume. And let's see if the optimum now gets changed or something. So these are called sensitivity analysis. Someone asked me, is that sensitive? But the sensitivity analysis is this. After you found the optima, you try to figure out what is important, what is not, what if I change this, what's going to happen, without doing any further optimization. So if you see that at your optimum a constraint is inactive, you have the freedom to change its right hand side, change the constant, because having this or not having this at this point was an unimportant matter. Now let's try to make it important by relaxing something, either the resource or the material or whatever. So these are very good information. Sometimes in the literature they are called as binding and non-binding. Binding means active, non-binding, as the name says, that the solution lies on the constraint, so it's kind of binding, and if it's not, then it's non-binding. But how about the equality constraint? For equality constraints, every equality constraint is active, has to be active, because there is no scope here of it being not equal to 0. So every equality constraint by default for any feasible solution, including optimum, has to be active. Okay, I mentioned 2 types of constraints. I also talked to you about equality constraints. Sometimes if it's very nonlinear, they make things very complex. So we try to relax the constraint by introducing an epsilon and converting an equality constant into two inequality constraints between minus epsilon plus epsilon instead of having 0. But I also mentioned if your equality constraint is linear or quadratic, that means you can replace one variable with the constraint. It's always helpful. So not all the time equality constraints are bad. Sometimes they are if they are highly nonlinear, but sometimes they are bad. And we have checked on the first day tutorial, we have looked at the exercise problem where we are replacing some variable with equality constraint. Okay, variable bounds, some algorithms require you to use as constraints. Some algorithms do not require you to use as constraints. It makes sure that no solutions outside the bounds are created. But all classical methods do not guarantee. So if you're using any point-by-point classical methods, the ones that we're talking about, you have to treat them as constraints. So here, one variable bound like this with lower and upper bound actually will introduce two constraints, right? One is xi greater than equal to xil, another is xi less than equal to xi upper. Okay, so each constraint will have two, each variable bound set will have two constraints introduced. Okay, now what are the properties of optimal solutions? So that's what we'll be talking about. Anything? Switch off my mobile. Okay. Okay. Thank you. All right. So what properties of X is going to satisfy the optimality, an optimal point? You have seen in the case of unconstrained problems that they were very simple, involving gradients. Here also they involve gradients, but it's much more complex as it's expected to be, right? First thing is this equation. This is called equilibrium condition. Okay, you see we have the del fx, the gradient of f. We now have the gradient of the constraint functions as well. So remember, there are j inequality constraints. So each of them is involved with a multiplier called Lagrange multiplier. So a constraint, jth inequality constraint has a Lagrange multiplier uj. Okay. Similarly, every equality constraints hk has a corresponding multiplier called vk. These are called Lagrange multiplier. Okay. The minus sign here comes because of the constraints are written in greater than equal to from. If you write constraint is less than equal to from, they will be plus. This is how it will differ from textbooks where they use less than equal to sign here. Okay, so now again, I'm not going to give the proof of that. You can find this in advanced books. So this is called the equilibrium condition. Now the other set of conditions that are there are the feasibility conditions. So as I said, every feasible optimal solution has to be a feasible solution, right? It cannot be infeasible. It cannot violate any of the constraints. So these constraints, all the j constraints have to be satisfied, all the k equality constraints have to be satisfied. So these two together are called feasibility conditions. Now these are something new. Okay, this one is very important. It's called the complementary slackness condition. Okay, what is that? For every inequality constraint, when you multiply with the respective Lagrange multiplier with the actual constraint value has to be 0. So what does it mean? When the product of two things are 0, either uj is 0 or gj is 0 or both are 0, right? So when is gj equal to 0? When the x is active, right? When it falls on the constraint boundary. So when gj is 0, uj need not be 0, or it can be 0 as well, but usually it is not. Now when gj is inactive, that means the uj is going to be 0. That means x is not on the constraint boundary. That makes that constraint unimportant, right? What is the value of uj? Has to be 0 in order to satisfy these conditions. That means what it says, if your constraint is inactive, its corresponding Lagrange multiplier is 0. Okay. If Lagrange multiplier is 0, what happens here? That particular constraint derivative is not needed in the equilibrium condition. So in other words, saying that constraint is not needed, because as soon as u is 0, everything related to that jth constraint is not appearing anywhere. So that means even if you take it out, you're still going to satisfy the optimality conditions. So that's why it's very, very important. It actually says whether the constraint is important or not at the optima. Is that clear? So for any constraint, if the Lagrange multiplier is 0, it's unimportant. All right. And then this is another important result, is that every Lagrange multiplier for inequality constraint has to be non-negative. It cannot be negative. There is a reason for that. There is a geometric reason, or it comes from the proof as well. But there is no such restrictions with V, with the H. You see, I don't have anything with Vk times Hkx should be 0. No. So for equality constraint, there is no such restriction, these two restrictions. Only for inequality constants are restrictions. So in this class, I think it's enough for you to know that the conditions, and you don't need to know where they are coming from. All right. Okay. Now, if a solution X, so let's say you found a solution by using an algorithm, and at the end, the algorithm give you the solution X. Now you want to say, is it really the optimum? Because the algorithm has given me this, but is it really the optimum? The only way to check is come here, come to this condition. So X is known here to you, right? X is coming from the algorithm, or you are suspecting a solution. You are a designer, somebody comes and tells you, hey, how about this solution? Have you looked at this solution? It looks to be a good solution. So that's your X. And now you want to plug in these conditions to see, is it really an optimum or not? So only thing you don't know here are the U's and V's, because X is given like that. F you already know because you have a formulation. G you already have, all G's and all H's you have, so they are gradients you can compute. X is supplied, so only thing unknown is U and V. So now you look for that X, you look for an U and V vector, okay, which will satisfy all these conditions. If you can find such a triplet for a given X, U and V, that satisfies all the conditions here, then that triplet is called a KKT point, Karush-Kuntakar point, by the names of the people who developed it. Okay, and this is a big thing in mathematical optimization. This KKT, there are lots of theories with KKT points. If you take a course in optimization and haven't heard the word KKT, then you have not learned anything. Okay, so you need to know what is KKT. So it is as simple as that. Okay, that I just mentioned. Now, a KKT point does not mean, that means a X, for a given X, if you can find an U and V that satisfies all of this, that's a KKT point, does not mean that X is an optimum point. Okay, it is a candidate for the optimum point. Like we have in the unconstrained optimization, if del f x equal to 0, the first order condition, which are also known as stationary points, if those stationary points are found, they all need not be minimum or maximum, right? We have to go for the second order condition. Same thing over here. Before you go further, let's try to see if it defaults to unconstrained theory that we know now. So in unconstrained problem, there is no G, there is no H. So capital K is 0, capital J is 0. So this thing drops out. So what is the condition we've got? Del f x equal to 0. That's the first order condition we knew, right? For multivariable optimization. How about this? This doesn't appear because there is no G, there is no H, there is no G, so this is not there. There is no G, so there is no U, so this is not there. So whole thing kind of defaults to del f x equal to 0 for unconstrained multivariable optimization, and that is what we have seen. Now this is really lots of additions that we have from there, but it kind of defaults back over there. There are higher order conditions with second order derivatives, but this is so ugly, I'm not going to show it here to you. And also they are just for theoretical purposes. So they are never really used in practical problem solving. So if this was a course on mathematics, we would have discussed all that. Okay. Now just to remind you that all the variable bounds have to be treated as inequality. So your inequality constant G is going to get more, has to include the variable bounds here, okay, in this formulation. Okay, I just want to take the equilibrium condition because that's the most important condition out of all that we have. If you rewrite and take the del f on one side and the del g's, let's say there is no equality constants at this point, only inequality. So this is the condition we get. So what it's telling me is that at the optimum x, because an optimum, it has to be a KKT point, right? The gradient vector, the negative of the gradient vector at the optimum of the objective function has to be a linear combinations of the gradients of the constrained functions. So let's try to understand what's happening. Let's say this is one of my constraint boundary. This is another of my constraint boundary that says this side is feasible and that side is feasible. So now if I take the gradient of that, because the gradient is positive here, the function values are positive here, the gradient direction will be orthogonal to this line, right? So negative of the gradient G1 will be that. Okay. Similarly, the gradient of G2 will be positive this way and negative of that is this direction. So this is my minus del G1, this is my minus del G2. Okay. So minus del G1 minus del G2, and U's are non-negative, remember? So if I do any linear combinations of those, where am I going to fall? In this region, right? So this says if my minus del fx, that means negative of the gradient of the objective function, falls in this blue region, you've got the optima. So that means what it says is this is the direction for the first constraint. If you go, you are not going to remain feasible, because for feasible you have to be this side. So that direction says you are going to be infeasible. This says you are going to be infeasible. So this region says you are going to be infeasible when you are in any of these region, and the minus del f means where your function value drops. That is that direction. Orthogonal to this is function value increases, but I am minimizing. So it says that the only way from this point your function value can improve if you are infeasible. What does that mean? So I told you something in words, right? I have a point here I have reached. This is my point I reached, which says the only way your function value will improve if you are infeasible. So what does it mean?
There are no better points in the optimal.
There is no better feasible point
In the optimal, in the feasible region.
in the feasible region. Yeah. So what does it mean?
The most
What does that point mean? What is this point telling us? Huh?
itself is optimal.
That is the optimum, is it not? Because I've got a feasible region, there is no other point better than it in the feasible region. So what does it mean? It's another way of saying that's the optima, right? Because if there is another better point in the feasible region, then my current point is not the optima. That point is the optima. But what this is telling me is the only way you can improve you can reduce your function value is if you are not in this region. You have to be infeasible. So that means it's the optima. You hit the optima. So the equilibrium condition actually tells you that it comes up with a situation where your negative of the gradient of your objective function is a linear combinations of negative of the gradient of the constraint functions. All right. So it's a mathematical way of saying that you have reached a point where no more improvement is possible by violating any of the constraints. So that means that's the optima. That's really the definition of optima. Okay. So equilibrium condition is very, very important. This condition has to be satisfied. I'm not sure if I've included those theoretical results here in this whole course, but we have actually dealt with these conditions quite a bit. These conditions are there since early 60s. These KKT conditions were developed in late 50s, early 60s. Okay, so more than 50, almost 60 years ago. Only 5-6 years ago, we had discovered that these conditions are singular conditions. What it means is, so let's say this is the optimum. Okay, let's say this is an optimum or a KKT point, let's say. And we know at the KKT point, all these conditions have to be satisfied. Okay. Now, I give you a point, epsilon from the KKT point, epsilon from the optima. It's feasible, let's say. So, it satisfies these feasibility conditions. Obviously, the equilibrium condition is going to be not satisfied now, because now there are better points. And epsilon away, I have a point that is better than my point, and also it's feasible, right? Because I have gone little worse than the epsilon and considering a point there. Okay, so to show you here this point, so this is my feasible region. Let's say I take a point right here. This is my optimum, let's say, and I've taken a point right here, very close to it. So now this will not satisfy this equilibrium condition, right? Because it is possible for me to find a point which will be better function value and also feasible. So obviously this condition is not going to satisfy. Now you may think, okay, at that point, if I assume how much is the violation, so left hand side has to be equal to right hand side. But let's say I define the difference as an error of how much dissatisfaction of this condition. If you compute the error here and you go a little further, maybe 2 epsilon, and compute the error there, the point at 2 epsilon may have a smaller error than the point at epsilon. There is absolutely no monotonicity of the violation of this constraint, this condition, as you go away from the optima. So these properties are only valid at the KKT point. It is not a local property. So what does this mean? This means that if only by an algorithm you have found the optima, these conditions will say yes, this is an optima. But if you are epsilon away from it, they may say no, you are violating like a massive amount. Or even if you are far away from it, it might say, oh, you are violating by a little amount. Okay? So they are not very reliable in the sense of if you have not found the optima. So they are singular conditions. They are all fine at that point. If you have the point, everything is fine. But if you're not, but when you are dealing with approximate algorithms that can find a near optimal solution, these conditions to me are useless, as they are. But this is what they have for last 60 years. Only when we have worked on it, we found there are some people in Brazil from mathematics department, they are trying to talk about it, approximate KKTs. So there is a, now there are, so this is about 3-4 years ago. So now it's kind of catching up, and there are quite a few papers on approximate KKT. If you Google there, you will find approximate KKTs. There are a lot of theories that are coming out. So approximate KKTs try to modify these conditions in a way that there will be a monotonicity principle that is kind of preserved. So a theory that is old doesn't mean it's all taken care of. I mean, you need to think of it, you need to look at it from your point of view as how you are going to use it. How is it useful to you? Okay. So to me, if I'm using it an approximate algorithm, I am never guaranteeing to find the optima. And then I need some measure to say how far away I am from the optima. Am I getting towards the optima? And then I need a metric that will tell me, yeah, you are progressing towards the optima. If some metric cannot give me that, then it's useless to me, right? All right. So let me reiterate again, a KKT point does not mean it's a minimum. So there are some more stuff that needs to be satisfied. So here is a small example I'm taking. In the afternoon, you are going to, before the quiz, you are going to solve at least one problem with these KKT conditions. So let's say I've got a linear problem here. Minimize minus x1 subject to this condition, constraint, and this constraint. So if I show you this constraint is actually this line on the x1, x2 space, and this constraint is this line, and this is the shaded region is the feasible region. I am minimizing minus x1 means I'm maximizing x1. So that means in this region, if I maximize x1, what is the solution? This point, 1. x1 equal to 1 and x2 equal to 0 is my optima. Now let's go and check that. So x1 equal to 1, x2 equal to 0. Let's see if that's a KKT point, because by theory, every optimum should be a KKT point, but not the other way around. Not every KKT point is an optimum, but an optimum has to be a KKT point. Okay, so at 1, 0, we are going to apply now the KKT conditions. So what are the KKT conditions? For that I need delta G, delta F and all that. So after I have done that, delta F is here, minus U1 delta G1 minus U2 delta G2 equal to 0, and all these conditions. When you try to solve all that, you find that, yes, I can find U1 equal to 1 and U2 equal to 0. That means I could find a U1 and U2 that satisfies all the KKT conditions for this point. That means it's a KKT point. So that's a way of showing that an optimum point is always a KKT point. All right. Now let's look at another point over here, which is not an optimum, right? We know this point is not an optimum, but it's on the constraint boundary. I took 0.2, 0.8, and I keep applying this KKT condition. This is the equilibrium conditions and complementary slackness. This point is already feasible. I find that U2 is equal to 0, and U1, one condition says U1 should be 1, another condition says U1 should be 0. So that means I have a contradiction, which means that I cannot solve for this point. I cannot find a one unique U1 and U2 that satisfies all the conditions. That means it's not a KKT point. So since this point is not a KKT point, immediately you can say this cannot be an optimum point. So for an optimum, it has to be a KKT point. So you can use the KKT conditions in a negative way. If it's not a KKT point, you can close your eye and say it cannot be an optimum. So this point cannot be an optimum. Now this point we found to be a KKT point. That doesn't mean it's an optimum. But now that I plotted it and I see it's an optimum, it kind of verifies this. Yes, this is the optimum. But I'll show you a case where it's a KKT point, but it's not an optimum. All I do is I change this constraint here. Now my objective function is same. I make the constraint a little complex. For all these exceptions, you need a complex function to show. But math is nice. Is that you can find something that doesn't satisfy the theory, and it's just a matter of finding it. So let's say if I have this constraint here, and I apply now 1, 0. So I do 1, 0 again. Now in this case, it says u1 should be equal to u2, but they has to be -1. Now remember, both u's have to be non-negative. So that means at this point, the KKT conditions are not satisfied, which means this point is known to be not a KKT point. But that's the optima, right? Because this is the feasible region and you are maximizing x1, so that's the optimum point. So although it's an optimum point, it's not a KKT point. So I take it back a little bit what I said, that every optimum has to be a KKT point. Well, there are some other thing that has to be satisfied before we say that. So I am not telling you everything in the beginning to make it less complicated, but now we are getting there. So first thing you need to do before you do anything with KKT is what is known as a constraint qualification condition. So that's another thing. And there are number of constraint qualifications. The one we'll mostly use is called linearly independent constraint qualification. So what it says simply is that the constraint gradients at the current point has to be linearly independent before you can apply the KKT conditions. Okay. In this case, I've shown you here that del G1 is this direction, and minus del G1 and minus del G2 is this direction. Are they linearly independent? No, they are the same directions with the minus sign, right? So they're not linearly independent. Since they're not linearly independent, I cannot use KKT conditions. So all this theory that I told you that an optimum point is always a KKT point is no more valid. It's valid only if del G1 and del G2 are linearly independent. So that's a caveat that you have. First thing you need to check is if they're linearly independent. So here is the overall necessity theorem that is valid. So if you follow this, you are fine. It says that if f, g, and h are differentiable functions, because we need to compute the derivatives, and x star be a feasible solution, has to be a feasible solution, let I be the indices of all inequality constraints which are active. Okay, so g at x naught at x star is 0. That means so these are all the active constraint sets. Yeah. Furthermore, the gradients of all g's, those are active. Inactive, I don't care. All the active is, that means all the constraints for which x makes gx equal to 0. If I compute the gradients of those constraints and the gradients of the equality constraints at that point, so there are several gradients we have, right? All the gradients of inequality constraints which are active and the gradients of the equality constraints, if they are all linearly independent, that's a very important thing, right? They're linearly independent. Let's say that's assumed that they're linearly independent. Then if x star is really the optimal solution of the problem, there exists a u star v star, always exists a u star v star, such that the triplet satisfies all the KKT conditions. So is that clear? So it's coming from knowing that the point is an optimum, knowing that delta G1, delta G2, all active gradients of active constraints, and all equality constraints at this point, their gradients are linearly independent. If they are known to you and the point x star is a feasible point, then it says it has to be a KKT point if it's an optimum. Nothing else you can say. You cannot say in a positive way that is this point, I found it to be a KKT point, is this an optimum point? No, KKT point doesn't mean optimum, but that's why this is called a necessity theorem. A point to be an optimum, it has to have this, that all the constraint gradients are linearly independent, it's a KKT point and feasible. Is that clear? So you see, as soon as the constraint comes in, things are not so easy anymore. I mean, there are a lot of ifs and buts. But we are talking about now, this theorem is not for linear or anything. It's for any optimization problem with continuous variables. It's nonlinear, any kind of objective function. So it kind of covers everything, okay? Much more than linear and other things. So So there are lots of ifs and buts that you have to satisfy. Is that clear? Okay, I think I mentioned all this, so I don't need to continue with that anymore. Okay, there are sufficiency theorems as well. Okay, sufficiency means, okay, I use the condition like the second order condition. So first order condition is always the necessity condition, that a point to be an optimum for an unconstrained multivariable problem, gradient vector has to be 0. That's a necessity condition, has to be 0. But any point that makes gradient 0 does not mean it's a minima. We need the sufficiency theorem, which means now the second order condition has to be computed, second order matrix has to be positive, definite. Then it pinpoints and say, yes, this is the minima. We have something like that also for constraints. But as I said, the generic formula is very, very complicated. I'm going to show you a very special case. If fx is convex, now if you're doing minimization, a convex function is a function that takes the shape of a bowl. I actually tell my students that it's a function that can hold water. So if you can put water and it holds it, it's a convex function. If you function like this, it's not. Okay. Every gx is concave. The way I have formulated that gx has to be greater than or equal to 0. Concave means it's non-convex. It's just the other way around. Okay. And every hkx, the equality constant is linear. If your problem, so you're solving a problem, you formulated it and you found, my objective function is convex, my constraints are all, inequality constraints are all non-convex, which is concave, and my equality constraints are all linear, then you should immediately, this theorem should remind you that any KKT point that you found with this is an optimal point. In fact, when all these conditions are satisfied, there can be multiple KKT points, but usually there is one KKT point. But multiple KKT point with the same function value can happen as well. So here is an example. This is a convex function in x1 and x2. Linear can be considered as both convex and concave. So this linear and this is a concave inequality constraint. This is a linear equality constraint. So if you can find the KKT point of this, that is guaranteed to be the optimum. Okay. So this is one of the sufficiency theorem, but very much restricted. If you look at the optimization books with theory, they mostly hover around these kinds of properties of problem, because you cannot really go too much away from violating these conditions and have a theory of sufficiency. Okay, but I can give you a simple engineering problem like a beam design or something which will not satisfy this. So then the question comes, how can we guarantee that a solution I've found is an optima? Well, there is no guarantee. You only have to go is, you can say that it's a likely candidate. Like you can find it to be a KKT point, and then they'll say, okay, this is a likely candidate. So whatever you found, at least a KKT point. Okay? And there are many algorithms that exist in the literature that attempts to find a KKT point. They don't even look for using sufficiency theorems or conditions because they're so complex. They say, okay, in practice, so many constraints are there, it's rare that you will find multiple KKT points. Okay? So if there is a KKT point, that's really likely to be an optimum. But another bit of caution here, every local minima is a KKT point as well, because the whole thing is with the derivatives is local information. So every local and global optima are KKT points as well. Okay. Any questions so far? Okay, I'm not going to dwell on this Lagrangian duality principle too much, but just to tell you that, because some of you may be a little math oriented, there is a whole kinds of bunch of literature on duality theory, simply because every optimization problem can be looked at from 2 points of view. One is this primal problem that we are currently looking at, minimizing fx subject to constraints and all that. I have deliberately not put the equality constant, but you can add it. And this will have a solution xp. Let's say this is called the primal problem, so I'm putting subscript capital P to say that it's a primal solution, and the corresponding function value is fp. For every such problem, there exists an equivalent problem that's known as a dual problem. Okay, what are the variables in the primal problem? All the x's, and x's are dimensions, materials that we've looked at in the first class, right? So this could be 50 to 100 different variables. How many constraints do you usually expect in a problem, in a design problem or any problem, you won't expect it to be as large as the number of variables, right? It'll maybe 4, 5, maybe 10, where your number of variables can be 20 plus, right? A typical problem. So your number of constraints are usually smaller than the number of variables. Now what is happening in the dual problem is the variable of the dual problem is the number of constraints, the Lagrange multipliers that we talked about, U's. So the U1, U2, these are the variables in the dual problem. So their number is as many constraints as in the primal problem. So since the primal problem has less number of constraints, this problem has less number of variables than the primal problem. Okay, but the objective function is a bit complex. Okay, so there is always a trade-off. Okay, so here for minimization of fx, the dual problem says maximize theta, and theta is defined here, subject to, and the variables here is a lambda. Here I'm calling them as lambda, but they're actually u's. U1, U2. Lambda vector is U1, U2, U3. Lagrange multiplier corresponding to a particular constraint. They have to be all positive. So this actually says is the real space m dimension, where m is the number of constraints and plus means they are in the positive side. Okay, now the theta lambda is defined this way. It's an infimum of the Lagrangian function which is given here, fx plus the u times g. Remember the equilibrium condition now. Now here you see this is the first time I'm putting a less than equal to sign. Okay, I want it to be a little close to the theory that in the book here. So this is less than equal to, when I told you that this is less than, in the equilibrium condition that becomes a plus, right? Let me go back because I'm waving a lot of things here. So this is my equilibrium condition, and this is for greater than equal to sign. You have a minus sign. If this is less than equal to, this becomes plus. Okay. So now look at this. If I ignore the equality constraint, this is actually the derivative of f plus, or in this case minus, u times g. If you take a derivative, then f becomes del f, u becomes del g, and this remains the same. That is exactly what is written here. If you take a derivative of this with the minus in mind, because if I change the sign, then you will get back the equilibrium condition. Okay, so basically this is coming from there, f plus this thing. So now all you have to do here is you find for every x, for a given lambda, for a given u vector, you are finding what is the minimum value of this for any x that you have. Okay, that goes as your theta for that lambda. So here your variables are u's. For a particular u, the way to compute theta is for every x you compute this sum, and the one that has the smallest value, that becomes the theta. So it's a nested optimization. This is also known as a bi-level optimization. There is one optimization here, maximize, and one is here, minimize. Infimum means minimize. The difference between infimum and minimum is that a minimum is a bounded number, right? When you say this function is a minimum, that means the minimum value is bounded to some finite number. Infimum, it can be minus infinity. That's the difference. But so this can be minus infinity as well. Okay, so it's a bit more complex to really comprehend the whole thing, but it has a solution theta lambda d, the dual solution, and theta d. Now there are certain nice properties of the two. So given a problem here, you can write this problem, okay, as a dual problem. The advantage of the dual problem is the number of lambdas are very few compared to the number of x's that you have. But the objective function is a little difficult to compute. It's just suddenly become a bi-level problem. But the properties are interesting. The difference between the fp and theta d is always positive here, and that's called the duality gap. But that's not important. The important thing is this. If you take any x from your primal problem, let's say that's a feasible solution, and you take any lambda that is feasible to the dual problem, this weak duality principle says that the corresponding function value is always greater than or equal to the corresponding theta. So it can be any x and any lambda that are feasible in their respective problems. This condition is always satisfied, meaning that duality gap is always greater than or equal to 0. Okay. Strong duality is something to do at the optima. At the optimum of the primal problem, the function value is also strictly greater than or equal to the optimum of the dual problem. But A special case is that they're equal. And when this happens, the duality gap is 0, and this happens for that convex problems we talked about. If your f is convex and every g is convex in this case, because I'm writing this as a less than equal to sign, then so for convex problems that the theoretical optimization people are really interested in, the duality gap is 0. So the implication is tremendous. That means that given your problem, you don't go and solve your problem, but you formulate a dual problem because it has less number of variables. If you can solve this problem, then you get a theta d, right? That is exactly equal to fp. So let's say it's a design problem with cost you are minimizing. So objective function is cost. But you didn't solve that problem. You solved this problem, and you found an objective function value theta d, which is, let's say, 1,000 rupees is the cost of that. Now you know if these are all convex, fx is convex, it's a convex problem, then you know that 1,000 rupees is also the optimal function value of your original problem. By not solving it, by solving another problem, you could relate what would be that. It's very interesting. And then there is a relationship between these two also. Once you found that you can compute xp from here and you can solve it in a quick way, okay? But unfortunately, if your problem is not convex, that condition is not true. But there is another nice thing is true. That is that if you found this to be 1,000 rupees, you know now that your f star, your actual cost, optimal cost, is greater than or equal to 1,000. It cannot be less than 1,000. So if you are looking for a quick answer of what is the minimum cost of this product I can have, if you solve the dual problem, it gives you some number, and you know that it cannot be less than this. Now, if that is already too high for you, before you do any optimization, any fabrication or anything, you can say, no, I need to change the design. I need to change some parameters, maybe material, maybe dimensions, conditions I have to change because it's too costly it will become. So this could act as a shortcut to getting a lower bound on your objective value. Okay, so these are very important things. But we used it in another scenario in a very nice way. If you have two processors, okay, in one processor you solve the primal problem, another processor you solve the dual problem parallelly. Okay, once in a while you stop and see what is the dual problem found so far, what is the primal problem, and this weak duality says that the primal one has to be always greater than the dual, no matter what feasible solution either have. If you see any discrepancies that no, this is not getting satisfied, you should stop your run and figure out what is wrong. Okay, maybe some formulation problem. So you can have checks and balances as you're running. You don't have to wait till the end to figure out something was wrong and the whole 2 days was lost in running it. The other important thing is, I'll show you some results here. So this is what happens. This is the result of running the two parallelly. So this is the dual problem running, and it's maximization, so it's increasing, you see, with iterations. And this is the primal problem running, and they are reducing, going to their optima. At this 11th iterations, they found to be the same. Now this is a convex problem. So I know that they will be exactly the same at the optima, and I get that. So this is another kind of checks and balances, or kind of proof that I may have done something right. This optimization problem I solved probably correctly because both of them are matching, and it's not a magic that two different runs giving you the same function value at the end. It's probably that they are at their optima. That's why it's happening, right? So this is just another way, because anytime you do optimization, and if you don't have any proof, you're dealing with algorithms without any proof, you're always under that pressure. Somebody can ask you, how do you know this is the optima? Oftentimes they ask this. So all these theoretical results, if you use in a nice way to counteract and say that, yes, I've done this and this satisfies my theory, I've done that. And next thing I'm going to do, take this point and try to satisfy and see if it's a KKT point. So all these cannot be all wrong. So the duality comes you this way. But if the problem is simple like linear programming, those of you who have done linear programming, a full course, I'm sure you are told about the dual way of solving linear programming as well, because linear programs are always convex. So all this sufficiency theorem and this duality gap is 0. So this is ideal. This kind of dual and primal problem solving together is ideal for linear programs and even quadratic programming problems. Okay, so to summarize L2, We've looked at direct and gradient based methods for constraints and unconstrained problems. Most of these algorithms, in fact none of them we talked about which assumes which can guarantee you global optima, but some of them have guaranteed to give you the local optima in certain problems like quadratic or convex. So my recommendations are single variable, use the golden section search, but before that you need to use a bounding phase. Cubic search is also very efficient. It's this Powell's kind of method. Then for multivariable, DFP and BFGS, these quasi-Newton methods are more efficient. MATLAB actually has a code called fmincon, and one of the options there is the DFP you can choose. And then we're going to talk about the constraint algorithm next. Okay, so this is the right time for me to take a break, and maybe the tea is waiting outside. So let's go for the tea. solutions. All right. So we looked at the theory for in a constraint problem. What are the properties of the point that would make it an optimum? But obviously, we are not going to be using those mathematical conditions to find the optima, as I have been telling you again and again. We always use numerical algorithms. So here is one or two algorithms that we'll talk about now. First is called the transformation methods, and there are a couple of methods there. I will talk about one. First one is the penalty function approach. Okay. So in the penalty function approach, there is a penalty usually added for a solution that is infeasible. If the solution X is not infeasible, if it's a feasible one, there is no penalty added. If it's only infeasible, we add a penalty. So obviously, it depends on the constraint violations, the constraint values that you have, and there is a new term called the penalty parameter. So I'm going to show you how to do this. There are two ways basically of doing. There is a third one as well. We're going to mainly stay with the exterior type penalty because it's easy to implement. Then there is the interior type, and then there is a mixed type, but we are only going to talk about the exterior type. So exterior type means that the infeasible solutions are penalized, okay? And in case of interior, even the feasible solutions are penalized if you are close to the constraint boundary. So as you are getting close to the constraint boundary, you're saying, no, you are getting to be dangerous now because you may cross the boundary, so we will penalize you, okay? So usually we don't use that in most of the optimization algorithms. It's the exterior penalty which is used. So I'm going to show you the principle of the exterior penalty next, but there are several penalty terms. This omega, that is the structure here, is R times hx square. If you have equality constraints, and this is exterior type. We take the absolute value if the constraint is violated. That's another exterior type. There is a log penalty, then there is inverse penalty, but we are going to be mostly using this bracket operator penalty. So this bracket operator says there is a bracket as you see here. The definition is this. This is equal to alpha if alpha is negative. Otherwise, it's 0. So I'm going to show you what's happening with this sketch. So let us say that, so this is the philosophy of penalty function approach. You should understand this, then you will understand other methods as well. So let's say I've got an objective function fx, okay, this solid red line. Where is the minima of that? Somewhere here, right? Here is the minima of that. This is the unconstrained objective function as it's called, and we have looked at all the theories and some methods of finding this particular point over here, right? Now let's say there is a constraint to the problem, and the constraint says this side is feasible, that side is not. Then is this the optima now? No. For the constraint problem, the optimum has to be a feasible one. So this is not the optimum. If this is monotonically increasing like this, where is the optima now? This boundary point, this blue point is the optima. Everybody understands? So you see now I cannot simply ignore all the constraints and only find the minima of fx for constraint problems. Constraints have to be taken into account because this is a typical situation that your optima lies on the constraint boundary. Wherever is the constraint, it happens to be the optimal solution. So now how does this algorithm finds this point A? A is now the optimum. How does this point finds it? So the way it finds it is in sequences. As I said, in optimization, it's all nested. You looked at multivariable unconstrained problem. It calls single variable unconstrained algorithm many times by line searches, right? Now we are in the constrained optimization. You will see that the constrained optimization will call multivariable unconstrained optimization many times. Each of them will call single variable unconstrained many times. So if you can do golden section type algorithm very fast, it has a triple effect, right? So it's all nested the way the whole optimization literature is. So let's see. So what it's saying is that first, you use, so we are using bracket operator penalty. So let's go back to the bracket operator. What does it say? Well, the bracket operator, here I am putting it as the square, but I need not also put a square. I could do 1, I could do 2, 3, 4, anything. So in that sketch I am doing with 1. The power of here is 1, but it basically says if your constraint is violated. So what is my constraint? Gx have to be greater than or equal to 0, right? That means Gx have to be positive for it to be feasible. Only when Gx is negative, then it's violating the constraint. And that's why it says if alpha is negative, this produces the negative value. And since I'm squaring, so negative becomes positive and multiplied by r. So a positive quantity is added to the objective function if your x makes gx negative. If your x makes gx positive, then it is 0. So then this is 0, then you are not adding anything. Okay. So what I have done here in this sketch is I have used the power of 1, and I have also made another change, is that I made alpha, let me go back, sorry, I made here a minus sign. Because I'm squaring here, that's why the minus or plus doesn't matter here. But if I'm using 1, then I have to put a minus sign here. Because if this is negative, I cannot just use the negative value here. I have to always use a positive penalty. So that's why I'm converting it to a positive penalty. Okay. So this whole region here is infeasible, right? Because this is the feasible side. So this whole region I don't want. Any point if there is, I have to add a penalty to the objective function. How much penalty? Depends on how much I am away from my constraint. How much is the constraint value? So you see this line here says r equal to 1, and this is how much penalty you are adding. So if you are so much gx, then your penalty is that much. So gx times r, and you get that much. If you are twice that, then you are twice going up. So it's a linear. So as you are violating more and more, as your gx value is more and more negative, that means you are violating your constraint more and more, you have a bigger and bigger penalty. Is that okay? But on the feasible side, there is absolutely 0 penalty. There is no penalty here. Okay. So this becomes my omega term, the penalty term. Now remember how that function is. This omega has to be added to fx. So if I add this function, this dashed line to this fx solid line, I will probably get something like this, right? So this dashed line here is my penalized function px, which is given here. Px, fx plus that straight line that we have. So these two when I add, I get my penalized function. Now what happens is in the infeasible side, I've got this line, sum of this solid red line and this one. What happens here? Here this dashed line is right here. So that 0 is added to fx stays fx. So px and fx are the same at the feasible side, but at the infeasible side, px is different from fx. Px is always more than fx. Is that clear? So now my overall PS function is this one up to here, and then remains the same here. So that is my px function. Now it's an unconstrained problem. So what I've done is I have converted all my constraints with the penalty and made an unconstrained function. Now I can optimize this using a multivariable optimization like steepest descent, like DFP, BFGS, all these we talked about, right? That cannot handle constraints, but we don't have constraints. We just now have this function to optimize. So when I optimize, what point I'm going to get? This point, the minima of that function, which is this, right? And when I'm optimizing this function with a multivariable algorithm, remember I need an initial starting point. Now instead of using a random initial starting point, I'm going to be using this point as my starting point, which I found in the previous iteration. So basically in this second stage, I'm actually going from this point to that point. Okay? Then next time I'm going to increase my r. When I increase my r, this function becomes now double. When I add this to this, this becomes this function, and my optima has moved slightly towards the constraint minima. Now I use this point and I find and optimize this function, and I get that point. This is how you'll be moving in sequences, starting from the unconstrained minima all the way towards the constraint minima. You do it in different stages. Actually, when you have very large r, let's say you go eventually r equal to 1 million or something, then your function will, this addition function will look like this because you have added r to very large, and now the function looks like this and this. So where is the minima? Right there at the constraint optima. So now what is the question you're going to ask me?
Why not take R maximum?
I always get that question, right? Why am I doing this way? Why not I just do it once? It's a very good question, right? What boundary condition?
Like if we take R more than enough, this feasible region will be thrust more inside the thing. So there's no
No. Feasible region is not changing. You see, fx.
Optimal point. That will be thrust more inside the.
If you take a small r, yes, like r equal to 1 and 2, your optimum is here, which is infeasible. But when you take r very large, like 1 million or 10 million, then you are pretty close. By the way, any r you take, your optimum is never on the constant boundary. It's always slightly on the infeasible side. But again, it's a matter of 2 decimal or 3 decimal places. It can be 2 decimal places inside. I don't mind it. Okay, so I just need an r that will make it up to that level. Then I'm fine, right? But that's not the answer. The answer is because we are using a computer. Okay, and how do we solve this problem? Let's say if we use the DFP or BFGS, which uses gradient, right? Del f, remember, del f would be needed. So here del p would be needed, the derivative of the p function, the penalized function, which has constraints and objective everything. We'll be doing it numerically, right? So when you do numerical computation at a point over here, let's take a point here, over here, you will take delta this way and delta that way. Take the difference, divide by 2 delta, and that gives you an idea of delta. Now, when you are dealing with this function and you have a point right here, one of them will come to be very large, let's say in terms of millions. Another one, just the objective function, which could be 5, 10, 100, whatever is the objective function that we're dealing with. So this number, when you subtract from 1 million, a computer will still give you 0 in many computers, unless you do very high precision computing, right? So the derivative computations becomes useless. And you don't get any information of the gradient close to it just because the function scaling is really bad. But if you now do this way, you are coming slowly. By the time you are here, your point is probably right there. That's your initial point. You're starting from there, very, very close to this point. So you are actually looking at this vicinity. So if I open up that function in that very small vicinity over there, the function may not be that bad. So your gradient calculations will start to work. The other issue is when you have this, you see that if my search space is from here to there, and I'm randomly creating a point, if this is the first function I'm trying to solve, I'm randomly creating a point here. If I'm here, what is the function value? I cannot even show it here. I mean, it just goes up. The function value is going to be very large value, and then all the computations are happening at these large values, so you may have some overflow error in your computer. Because you're dealing with a finite precision computer, dealing with very large numbers is going to be erroneous. To avoid that, people go slowly, so that every time you are going there, you are in the vicinity. You are not moving much actually when you are going. And initial one, you have a smooth function over the entire range. You can start with any points and you can optimize this because everything is in same scale. You have not added anything. So in this algorithm, you start with r equal to 0 or very small number, and then increase r at every sequence. And every sequence you will be calling a multi-objective unconstrained algorithm, which itself calls single variable unconstrained algorithm, and then you solve it. Is the philosophy clear? Yeah.
The calculation of the optimal point here, it involves gradient measurement.
Right.
But here when we add the penalty function, so there is a discontinuity.
Yeah, there will be a kink if you use if you use r equal to 1, and sorry, not r equal to 1. If you use the linear bracket function, but if you use a quadratic bracket function, then it becomes continuous. Then the derivative will exist. Any other question? Okay. So you understood the philosophy of this, why we are doing in a sequential manner, and the whole philosophy of how an unconstrained minimum will eventually get transformed into a constrained minimum. Okay. Here is an example. So this is the same problem I'm showing you again and again, because then you can see how the algorithms differ from each other. Now I'm adding a constraint. This constraint says this side is feasible. Okay. This was the original optima, but now it has moved there. Okay. This is now the minimum point, because at any other place the contour that it cuts has a higher value. This is the minimum contour that it cuts, and it's about 60. It's actually 60 point something is this minimum point. Okay, so this is the feasible region, this is the infeasible region. So this is when r equal to 0. So when r equal to 0, if I optimize, that means I'm not considering the constraint at all when r equal to 0. So I will get this point. It is equivalent to saying I minimize this fx and I get that point. right? So same thing here, I will get this point. Now what happens? Now I increase r to 0.1, r equal to 0 to 0.1. Now my contour looks like this. See, this is slightly different from what I had before. Look at these contours and look at this one. It's slightly different. Now the optima has moved here. It was at 3,2. It was here before, unconstrained. Now it has moved there. See, it's moving towards the constrained minima. Like there, it was moving towards the constrained minima. So now what I'm going to do, if I'm starting from r equal to 0, all I have to do is optimize from here to there. But in this simulation, this is my first step. I'm starting with r equal to 0.1, and I'm starting from an arbitrary random point and solving it. This is the steepest descent method I've used. Steepest descent method I've used, and I get this point. Now I increase r to 1. Look at the contour now. It's completely different. So I was here. Now I start from here, and steepest descent takes me there. So I'm already very close to the actual optima. Then I go r to 10. So here I'm multiplying 10 times r. You can also add by some amount. Now I go from here to there in 10. I didn't have to do anything more than 10. I get with the precision that I wanted, I got the optima. Look at the contour here again. These contour lines are parallel to this because these values are so high. If the way to visualize this contour is the whole surface is coming down to this circle, and then there is a minima towards this point, and then it goes up slightly on the feasible region. So there is a nice minima right over here. Okay, but the fact is that I'm now starting from here and going there. So these points being very high, like 5,000, doesn't bother me because my algorithm will never come here. Okay, I am here where the function values are already about 65, 75, something like this. So I'm staying in that range. So my algorithm behaves well. So doing it sequentially, it helps me get there. Okay, how to change r from a low value to a high value is an art, still an art, and you have to really experiment with it. So when I started my career in optimization, these are some algorithms that was the only things available. So we had to experiment quite a bit with this. So it would take me at least a day to figure out what is a good R. This is with one constraint, right? If you have multiple constraints, then you have to normalize the constraints, which I'm going to talk to you about. Then it gets even more complex. The way this philosophy works is that you had a unconstrained contour surface function, right? Now, as you are adding this penalty term with up r, you are actually changing your function. And there is a lot of distortion in the infeasible side. You see how the distortion is from here to there to there. There is a lot of distortion. So what it does, the way I visualize it, is that you had an unconstrained minima here, but the constant minima there, the function is getting twisted so that its optima goes towards it. It's twisting itself, and by that process, the optima is moving. It's sort of like, the way different continents came together and formed Himalayas and things like that, very similar. You are twisting the function in a way so that your minima now, instead of maxima, the minima is now going towards the constrained minima. That's how you can visualize this whole penalty function thing. Now, in that twisting process, if you have lots of constraints, every constraint is introducing a term in the twisting process. Now, there could be artificial minima, like artificial lakes that are produced by this process, and multiple peaks and hills and all that has formed. These are because of interactions of multiple things. And that similar thing happens here as well. And so this algorithm can get stuck here and there because it's producing a lot of artificial minima. But even then, this is still one of the very popular methods used in practice. Okay, when we have multiple constraints, what to do? So let's say one of my constraint is related to the strength of a member. And the strengths are usually in megapascals, right? If you're doing the SI unit. So usually the strength of steel is about 300 megapascal. So you're saying the stress should be less than equal to 300. And you may get a stress that is 350. So there is a 50 times 10 to the 6 is your violation. Because you want it to be 300, but you got 350. Now you have to increase the dimension of your member so that the stress comes down. Let's say I have another constraint that says deflection of some part of that member should not be more than 5 mm or 10 mm, let's say. How much violation are you expecting there? Okay, instead of 10 mm, it can be 20 mm, or it may be 15 mm. So there may be a 5 mm difference. So one constraint says the constraint violation will be 5 mm, 5 unit. Another says going to be 50 to the power million, 50 million. So if you just simply add the way I've suggested in the beginning, like here, here, I didn't add up here. I didn't show you the add up, but basically you have to add up each of them. Where do I do it here? Okay, everything is 1 here. So yeah, here. So if let's say this hat is not there, if you have to have different constraint violation and you just have to add them so that then you multiply with R, that addition will not make sense, right? Because the violation on the deflection is negligible compared to the violation in the stress. So the way to have both of them important is that to normalize them, normalize the constraints. So if you have and there is no one agreement for the normalization. We also use different strategies, but somehow you have to normalize. Some normalization is needed so that the values are more or less the same. So what I suggest to do is if you have a constraint that says Gx greater than equal to Bj, so here the stress has to be less than equal to 300 megapascal, then what you do is you divide G by B, and so divide the whole thing by B, so Bj here, so you get Gj by Bj, forget the dash, and minus 1 comes from there, greater than equal to 0. So this becomes your constraint. So you see what I'm saying? The right hand side can be anything now, or every constraint could be different, but you divide the whole constraint by the right hand side. Now your violation, so your 50 million is now divided by 300 million. So you get 50 over 300. And then 5 millimeter violation divided by 10 millimeter violation, because 10 millimeter was your requirement. So now you get 5 over 10 and 50 over 300. So they are kind of comparable. Right? So that's the normalization you have to do, and I call them with the hat here. This is the normalized constraints. Then you apply them with the bracket operator to see if this quantity is less than 0. If this is less than 0, you put a minus sign here with that. And if it is greater than 0, then you put a 0 here. And then you can add all the constraints multiplied by R, and that's how you use it. So normalization is very, very important. Okay, so that's the penalty function approach. And as I said, that's very simple-minded. So if you write a code, in fact, my optimization book, I've been referring to my book, but it's a book which was published by Pratihar back in 95. Okay, it's still available here. I'm not sure. I think 1 or 2 professors are using that book for other classes as a part of another class, but some universities have adopted it. So this is about all these different optimization methods, the theory I'm talking about, very gently written for engineers. Okay, it's supposed to be for an introductory optimization class. So I've been referring that. So there, we talk about in more detail about some of these things. Although penalty function is very popular, it has this issue of a couple of issues I mentioned. Right, one is artificial minima that it produces, and it distorts the whole thing. But this method we're going to talk about next is called the augmented Lagrangian method, ALM. This kind of alleviates both the issues, and to me this is much better algorithm than penalty function. But unfortunately, because it looks ugly, not many people use it. It's just that they don't have the patience to understand the algorithm. But if you have to use one method of the two, I would suggest you use this. Okay, augmented Lagrangian. And also, not many codes come up with this, but this is really has a lot of nice things. I'll tell you what are those. First, let's discuss what that is. So this function, this is the new penalty function now. It's not simply fx plus r times the constraint violation. Here you have fx plus r times something more. You see, there are parameters like sigma j for inequality constraint and tau k for equality constraints. Okay, the way they're done. This is still the bracket operator. Okay. Now, sigma j's and tau k's are also evolving as you are running the algorithm. To start with, you assume both are 0. Sigma j's and tau k's are all 0 to start with. And then there are adaptation formulas. So sigma j1 comes from sigma j0, which is 0, plus whatever is the result at xt, whatever is the constraint violation. It comes from there. Similarly, tau k. So this is how you would update. So the idea is this. First you assume some sigma j tau k, and they are all 0 to start with. So these are not there, this is not there, this is not there, this is not there. So basically it's a penalty function approach. Fx plus r times bracket operator gx square. So it's basically penalty function approach. You solve it in the first sequence. Okay, in this method r is not changed. R is kept fixed. That's why we don't have any distortion. So not any distortion, minimum distortion we have. R usually you can fix to any finite number, but not 0. So let's say we keep r equal to 1. Okay. So now I have the almost, it's like the penalty function approach, and I start from x0 and I solve that problem. I will get an x1, right? After I solve this unconstrained problem. At that x1, I compute this quantity. This is still 0. I compute this quantity. That becomes my new sigma j. And I compute at this x1 hk, and I get my tau k. Now I substitute them here. Now they are no more 0. Okay? And then I solve this problem. R is still same as 1. Okay? I solve this problem. I get x2. I come here, compute sigma j with the x2 here. X2 here, I compute tau k. Put it there. Solve the problem again with r equal to 1. Same as before. So keep on doing these things. When eventually you see that xk is not changing, the xt value is not changing from between 2 iterations, you quit. Now, there are several positive things. First is there is less distortion of the function. I'm going to show you how it looks. Most important aspect, when it ultimately converges, okay, that solution xt is guaranteed to be a KKT point. There is a proof that it will become a KKT point. And you get back the Lagrange multipliers. So once you've gotten these sigma jt, that is at the end, whatever is the sigma g, say delta jt and tau kt, r you have chosen to be something fixed. When you compute these way, you get Lagrange multipliers for every constraint. This is a byproduct in which you can get the Lagrange multiplier. There are very few algorithms who can do that, who can give you the Lagrange multiplier. And when I talk about the sensitivity analysis, you will see how important Lagrange multipliers are. Penalty function cannot give you Lagrange multipliers like this. Penalty function doesn't guarantee that the final solution is a KKT point. So this one does both this. Plus there is less reduction in a reduction in distortion. So I don't know why people should not use this. But I think my hunch is that since it looked a little complicated, people avoid it and they don't understand the whole thing. All right. So here is the whole method. I'm not going to go through. These are actually taken from my book, which is really written in a step-by-step format, each of the algorithms. So if I try the same problem that I showed you for penalty function. So here is the feasible region again. This case I fixed r to be 0.1. Okay, so r 0.1. So here is with sigma equal to 0 and tau equal to 0. So this is what the contour looks like. So I get, here is my minima. So when I start from a random point, I get to that solution. Now I compute, there is only one constraint, so there is only one sigma. I compute that it was 0 before, now it's become minus 14.248. Next iteration, look at the two contours. There is not much distortion, right, between the two contours. And now my optima is almost moved to the constraint optima. And what is sigma 1 now? It's minus 22.836. I don't know whether I have one more iteration here. No, I don't have one more iteration. But it's already, oh yeah, I have here. Sigma 2, this, I'm not showing you the result, but I'm showing you sigma 1, 3. That's 22.836. See, they're almost converged, right? So I stop after third iteration because it's not going to change any further. So eventually this sigma converges to a value. Now I take that sigma and I used r equal to 0.1 and minus 2. This is the formula, and I can get the Lagrange multiplier back, okay, out of this. And this solution that I've got, eventually it is very close to this. That's guaranteed to be a KKT point. And remember, this is the optimal point, which is supposed to be the KKT point as well. So, this makes less distortion. It guarantees that it will be a KKT point, and you also get the Lagrange multipliers as byproduct. All three things are in one algorithm. Very few methods have that. So my 100% vote for using this, if you have to use one method, which is transformation method. Any question so far?
So what are the interior penalties?
Interior penalties are methods which penalizes infeasible solution, but that are closer to the boundary. So the whole idea of infeasibility is that if you go, you don't want to be on the infeasible side, right? So one of the interior penalty term I'm showing you here, I don't have a sketch for it, but I can plot it here. It's like, for example, the log penalty or the inverse penalty. So if I plot it here, so let's say that I do the same thing that I did before. Here is my unconstrained minima. Okay, I've got a constraint here that says the other side is feasible, this is feasible. Okay. Now exterior penalty always penalizes solutions on the infeasible side. Interior penalty will penalize solutions here. So interior penalty will look like this. That means these are feasible points. As you are getting closer to the constraint boundary, your penalty is more and more on the boundary of infinite penalty. So this is the inverse penalty. You see, the gx here will be 0 and gx here is positive. So this is 1 over gx. So when you have gx close to 0, you have very large value, and as gx is higher, it reduces. So the penalty reduces like inverse way, right? So what you do now, you add the two. Okay, so it's the same way you do that. So your px will become this. This is your px function. In this case, you start with a large r. You start with large r. So in the exterior penalty, we start with a small r and keep on increasing, and that's how we come this way. And in interior method, you start with a large r, and then you have a large value. Your optimum is here. Okay, then you reduce your r. Your function becomes like this. Now you come here. So you will be moving this way as you are doing with interior penalty. Eventually you will get the same answer, but two different ways. The advantage of the interior penalty is if you terminate at any intermediate sequence, you still get a feasible solution. But in exterior, you cannot terminate early, because if you terminate early, you are still in the infeasible side. You have to come close to the boundary before you terminate. So you need to go on with few iterations of r's. But here, if you all want is a feasible solution, you can terminate any point. But the interior penalty requires you to, so there are always pluses and minuses, okay? The interior penalty requires you to have an initial feasible point to start your algorithm. Interior penalty, you cannot start here because it's not defined. This function is not defined here. So you cannot start there. You cannot give a p-value to that. And in a practical problem, when you have 50 variable and 10 constraints, to get one feasible solution, you may have to evaluate like million times, million different solutions before you get one feasible. So getting a feasible solution to start your interior point method there is a waiting time. Many industrial problems I have solved where they say, I don't care about the optima. Can you give me even one feasible solution? If I give them a feasible solution, ideally they can implement it, right? Nothing is violating. The whole design is not going to break. It's going to satisfy all the conditions. It's just that I could have done better. But if I give them one feasible solution, that's still okay for them, all right? But finding such a solution is not easy. But an infeasible solution you can very quickly get by random means. You create a random combination of variables, most likely that's infeasible. And exterior penalty, you can start with that solution. But interior, you have to say, create a solution at random, and you check it and you say, no, this is infeasible. Create another one, no, infeasible. You have to do this maybe a million times before you get one feasible to start your algorithm. So these are the flip side, okay, that you need to understand. So interior penalty is not very practical. That's why I don't talk about it much. But exterior, easy to start, and it's a nice algorithm. As long as you keep running it, eventually you will get close to the feasible region, and it works. But the augmented Lagrangian method is always exterior type. Any other question? You have to do everything. So one simple thing is you just say minus fx. So if you're maximizing fx, you just convert it to a minimization problem. Say minus fx and use any of these methods. That will be my recommendation. Instead of changing the algorithm, you change the problem and use the same algorithm as for minimization. Penalty, then you have to subtract. if you want to just keep with the maximization. So everything changes. So I would not recommend that. I would say you convert your objective function to a negative thing and minimize. Any other?
So can we extend this algorithm for two objectives?
No. Well, we'll talk about that. First of all, you need to know what are the optimum for two objectives. So there is no straightforward way, but when we get there, we'll talk about. Hold on, write down somewhere and ask me the question again when I get to multi-objective. Any other? Okay, this is another very important step in optimization. It's usually called a post-optimality analysis. Okay, it's called the sensitivity analysis. Okay, and I have been referring this to you, but easily you can get confused with other things that we do. Sensitivity analysis, by definition, it's to analyze your optimal solution for its neighborhood. So obviously there is no other better point than that, right? You are now not trying to doubt this optimal point. Well, you can be. You can doubt your optimal point because you obtain by an algorithm. Now, if you're doubting and going and checking for the KKT conditions, going and checking with duality formulation or some other way, those are not sensitivity analysis. Those are like you are still trying to figure out the solution you found is the optimum or not. Okay? That's still your optimization process. That's a validation step of that. So when you have validated and you have the optimum, which you think, yeah, for all practical purposes, everything I have done tells me this is the best solution that I have got. Now you're happy with it. Now you're about to implement it, but you want to do few things before you do that. What are those things? You want to see its sensitivity with the parameters of the problem. Because in the formulation of the problem, you have fixed quite a few things, like material. You have chosen to be a particular type of steel. In that can design problem, we said we'll have to have 330 milliliter. Okay? And you got the solution. Now you're saying, what if I do 335? You don't want to do 400 from 330. That's too much change. Slight changes, or maybe I want to do 325 maybe, or 320. So so now you want to ask this question that I want to change some parameters on my problem, and I want to know how much will be the change in my optimal function value. First of all, is it going to be better? For a complex problem, it's not so obvious, but in the can design problem, if you want, let's say, a larger volume, do you expect your function value to be worse or better? It's intuitive, right, or not? So you are designing the can for minimum volume, or minimum surface area or cost, and you optimized it for 330 milliliter volume inside. You got the solution. Now you're saying, I want to make it 335. Do you expect the cost to go up or reduce? Why go up? Because volume increases. You need more volume. The volume increases, so you need more material to cover that volume. That's kind of intuitive, right? Now, in a complex problem, when you have 10 constraints and the objective function, which is cost or something, it's not so obvious that if you change this, whether the objective function is going to increase or decrease. So first thing you want to know, is my objective function going to get better if I change this parameter or worse? Second question is, if it goes up by, let's say goes up by how much? Can I get an idea how much? Is it 10%? Is it 5%? Is it 1%? Okay. Other thing you want to do, I want to simultaneously change few things. I want to change this parameter here of this constraint, that parameter there of that constraint, and few other simultaneously I want to change, and I want to know what will be the effect. Is it again going to, my function value is going to increase or decrease, and by how much? So all these analyses you want to do before you implement it, so that you know that you have made a good decision of those parameters also. That's under the purview of sensitivity analysis. So how sensitive is your optimal solutions with respect to the parameters of the problem? That's what it is. Okay, so once you understand the task, I can go back to my problem, let's say minimizing fx, subject to this constraint. Now I'm putting a right hand side. So it could be that minus of stress should be greater than equal to minus of strength. So in other words, stress could be less than strength. So this is the strength value that I'm talking about. And this could be some other equality constant. Volume should be exactly 300. So beta k can be 300. This is the volume expression. That's why I didn't say Gj. I put a dash here because the Gj will be G dash x minus alpha j. That will be my Gj. Okay, that's what I've written here, right? Okay, so this is the original problem. I've solved this problem, and I found an optima x star. And let's say I've also found the Lagrange multiplier because I've used the ALM method. I found for every constraint here, I found the u's, and every constraint I found the b. Okay. Now I didn't tell you that, but there is a definition of u that comes from the optimization problem. U is nothing but the change in f star with respect to the change in the right hand side. So it's also known as the shadow price in economics. Okay. So that's the basic definition of Lagrange multipliers. Okay. So that means if I change this by a small amount, how much will be the change in my f? That actually determines by, that's actually u. So you see how important that is now. So if I make now several changes to plus delta alpha j plus delta beta k here, if I change several of them or all of them, the overall effect from this formula with the chain rule comes out to be the overall change in the f will become this. And this is nothing but uj, this is nothing but vk. So if I know the Lagrange multiplier and the amount of change I want to make in each of these right hand sides, I can get an estimate of what will be the change in my optimal function value. Right? Here everything is assuming that these changes here you are making are very small, okay, not very large. So let me show you its effect on a problem like this. So this is a geometric problem. So here is my feasible space, one constraint and another constraint. This is my feasible region, and I have a point here 3, 2, and I'm trying to find out which point in this region is closest to 3.2. It turns out that this point, right? So you drop perpendicular to this line and it comes here. So that's from the Euclidean theorem like we talked about, right? So this becomes the optimum point. So when I solve this problem, so the way I formulate this, my x1 and x2 combination should be inside or on the boundary here. So these constraints will tell me that. So any x and y, x1, x2 that satisfies these two conditions means they are inside. And now for that x1, x2, I take the distance from here and I minimize that. So it's going to be this point, right? When I solve it. So when I solve it, I get this point. And when I do the Lagrange, augmented Lagrange multiplier, here is the result. I get my u1, this is my final solution. I get the u1, u2 computed from it is 0.802, u2 is 0. So you see, the first constraints I have a positive u1, u2 always have to be positive or 0. And u2 is 0. What does it mean? First, let's try to understand. This is my first constraint, which is this a nonlinear constraint. And this is the linear constraint, which is this. This is u2. This is the optimum. Now, is the optimum going to change because of this line? This point is not on the constraint boundary. So this is an inactive constraint as far as this optimum is concerned. But this is an active constraint for this optimum. So what do you expect for the u2 to be? 0, because this is not important to define these location of the optima. Is that clear? These are very fundamental ideas of optimization. So u2, then it's not surprised that we found u2 to be 0 here. But u1 is positive. Now let's say I had another situation where there was a constraint going through this point, another constraint. So this is also active. So I have this constraint and I have another constraint. The Lagrange multiplier for this constraint is 0.802. Let's say for the second constraint which passes through this point, the Lagrange multiplier was 2. So this was 0.8, that one was 2. Which one is more important? Why? Because of this relationship. So every Lagrange multiplier says if you change the right hand side by a small amount, by delta alpha j, how much will be the change in the objective function value, optimal objective function value. So if you have a large value here, larger value here means there is going to be a large change in the function value. So that means if I just change slightly that constraint, I can get a greater effect in my objective function value. So that is more important. So you're right. If the Lagrange multiplier is large, the absolute magnitude of the Lagrange multiplier, anyway, they're going to be positive, but for equality constant, it could be negative as well. So if they are larger absolute value, they are more important. So now if you've got 10 constraints, and for each of the constraints you found some use, some Lagrange multiplier, some of them are 0, that of course you're saying unimportant, and rest all that are positive, you can rank them according to the absolute value of their Lagrange multipliers. The one on the top with the highest value is most important. So now you can see what is that constraint out of the 10 constraints that I gave, and you can get a lot of insight why this is really so important for this optima. If you have a right hand side for that, you really want to make sure that is the right hand side you want to use, because if you can reduce or increase slightly from that right hand side, you can achieve a much better cost. So these are some ways you can go to your boss and say, boss, here this constraint that you said to me to put this right hand side, if you can sacrifice 1%, I can give you a 10% reduction in my objective value in the cost. And his eyes will be up and say, whoa, is that right? So let's then, okay, this one involves that department or that department. He will immediately pick up the phone and say, hey, you told me so much value on this maybe axle to axle distance. Can you even reduce by 2 inches? Because I can then reduce the cost of this car by so much, and then they negotiate. And they say, no, because if I reduce it 2 inches, my stability is compromised, so I can do 1 inches. You say, okay, then let's. So these are the starting points of some very nice, fruitful discussions you can start coming as a part of optimization. So you see, the optimization is not only giving you just the result, but it also tells you much more stuff about further discussions, post-optimality analysis, that can bring down costs, that can give you that knowledge. It's not only that you are doing it, but then it stays with you. Next time you do a car, you know that this in this kind of problems, this is the important constraint. So before you even start the next project, you start negotiating with the person that, hey, you are most important people to me, so make sure you're not asking anything extra, because your requirement controls how much cost I'm going to be. And then the next department is that. So if they are very adamant, cannot do it, go to the next department and see how much they can compromise. And as soon as you start doing these things, you see the effect on the overall product. The upper management will notice you, immediately notice it. He's the most important guy to me because he can understand what is the critical part of the whole system. So these are priceless information really coming out of optimization. There are so many parameters, constraints you have, and you are suddenly able to pinpoint where to concentrate. Right? So what I have done next in this is I said, okay, let me, since this one is not important at all, I forget it, I'm going to now fiddle with this 4 because this is my parameter. 4 set me up over here. If we set it to 3, okay, so I'll set it to 3 now. Where will this line go? It comes here. That's dashed line. So now I have a constraint that says anything below this line is feasible, and this constraint says anything above is feasible. So now I have a smaller region, and I'm still solving the problem, finding the distance from 3 to. So where does the optima go? Is right there. So now what happens to the distance? Increases. I wanted to minimize the distance, so I have an increase in distance. So this I'm seeing from the geometry, but let's see if my sensitivity analysis tells me. So what I have done, what is my outside? What is my right hand side? If I write this as this way, this format, okay, gx greater than or equal to alpha j, what is my alpha j? Minus 4. I have to take it on this side, right? Minus 4. Remember that. If I make it 3, what will be my right hand side? Minus 3. Minus 3. If I change this constraint to 3 here, then it will be minus 3. So I want to go from minus 4 to minus 3. So how much is the change? Minus 3 minus minus 4. That means plus 1 change. Plus 1 change, right? So the delta, I'm interested in delta alpha j. Delta alpha j here. So what is delta alpha j? Plus 1. Exactly. So that's plus 1. So remember that. So now I found U1 as 0.802. Okay, 1. And this is of course 0. I have not changed anything. So U1 times plus 1 is going to give me plus 8.802. So this analysis, sensitivity analysis tells me if you go from 4 to 3, so the constraint goes down, you are going to have an increase in your function value. You see, it predicts correctly, right? I have an increase in the distance. It also tells you by how much. It tells you 0.802. if you compute it, it's not exactly 0.802, but it's very close to that. Okay, so not only it has the ability to tell you which direction is going to increase or decrease, also tells you some idea of how much. So with this information, now your optimal function value I didn't compute here. The function value here, the distance would be how much? Maybe about 3 or 4, to maybe 3, let's say. So the actual f star was maybe 3. Do I have it here? No. Yeah, so it's about 3, let's say. And now I have 0.802 increase. So 3 point something, right? Yeah, so 3.8, let's say 4. So 0.8 out of 4, which is about 1 by 4. So it's about 20%. So about 20% increase. So these are the things I'm interested in knowing, right? So if I go from 4 to 3, I've got 20% increase. So that could be too much of an increase in distance. Then I might decide, no, I'll not go from 4 to 3. Maybe I go to 4 to 3.5. And then I can recalculate and figure out what percentage will be the change. So this is the negotiations that I've been telling you about, right? Okay, so that's about the sensitivity analysis. And then it's different from the other stuff that we often do to make sure it's an optima. Yeah.
So here they are doing sensitivity analysis on local optima.
Yeah.
Is it applicable for global optima?
It's applicable to any optima that you found. This is because everything is related to gradient. As long as you have the Lagrange multiplier found at that point, you could do the sensitivity analysis, right? So these are not particular to local or global for any optima. And if you have multiple optima, because each of them now are going to be KKT points, you could do the same analysis and every point will give you different answers, right? So it continues. Okay, let's continue then. So we looked at transformation methods. Under that, we've seen penalty function and augmented Lagrangian method. Now we switch gear from the gradient methods to direct search methods, or other methods rather. So this one we talk about is called the random search method. Was proposed back in '73 by 2 Finnish guys. It's a very simple-minded algorithm. That's why I try to tell this also. Different extremes of algorithms. What you do here is you create. So you have a box, either coming from the variable bounds. So every variable goes between a lower bound, upper bound, lower bound, upper bound. So you have a box. If you don't have lower and upper bound for certain problem, you have to assume some bounds and make sure that your optima is within somewhere. Okay. Once you've got the box, then you create p number of points at random inside the box. Okay. Locate the best point. Okay. Then what they suggested back in '73, throw away all the other points. Now I've got the best point somewhere. Take the box, reduce it a little bit, and center it at the best point. Again, create p points, repeat the process, find the best, reduce it further. So you are reducing the box size as is shown here, and you're locating the best and continue like this. Very simple-minded. If I give you in 10 minutes, you can write a code, right, and implement it. So there is no gradient, nothing. But it's not very interesting or efficient algorithm because you're throwing away so many points, right? You could utilize them in a nice way. When you talk about population-based methods later on, this is a precursor of that, but they are much, much more efficient. More information processing takes place in them, but this is a precursor. Okay, so I want to just tell you that there are algorithms exist like that as well. Okay, coming back to more sophisticated ones, again with constraints, things are very difficult, as I've been telling you. One of the ways people in the classical literature, so I consider the people who work in point-by-point methods with gradients, they are very close to the theory, right? Mathematical theory. They may not be all of them liking the theory that much or utilizing the theory that much, but they also don't want to deviate too much from the theory. So one of the things that we know in theory is that if I have a linear problem, like the linear programming, which we haven't talked about yet, but next we'll talk about that. So linear programming problems, there is a guaranteed proof, a guaranteed algorithm that's going to give you the optima, right? A simplex search method, for example. Now, why not, when I'm solving nonlinear problem, I somehow convert a linear problem, a nonlinear problem, to a linear problem and solve. And obviously, the linear solution to the linear problem will not be the solution to the original problem. So I have to do something after that and maybe continue in some iterations to do that. So there are quite many linearized search methods to solve nonlinear problems. So first thing you need to then do is understand how to linearize a nonlinear function. Do you know? You probably studied Taylor series approximation. You all know that, right? So you have an objective function which is nonlinear. You can take the first derivative, second derivative, and you only need first derivative to make a linear approximation, second derivative to have a quadratic approximation. Here is the linear approximation at x0. So linear approximation is done at a particular point. So you choose your current point. This is your actual function value at that point. Delta fx is the gradient at this point, and x minus x0. Everything else is known here except x. That's why it's linear. Although your original function could be highly nonlinear function. Okay. So you can linearize objective functions, you can linearize constraints, and then construct a LP problem. When you get the solution, it is not likely to be the solution of the original problem, but at this new point you can linearize your original problem again and solve it as a LP again. And you can keep on doing this. This method is called sequential LP or SLP. Okay. Frank-Wolf is one such method. Let me just describe to you the Frank-Wolf method first. So you're starting with the initial point x0. There are convergence parameters. You always have iteration counter 0. You're starting your algorithm. First thing you do is check the gradient. If the gradient is very close to 0, they are terminating. Although they should not, because gradient equal to 0 in an unconstrained problem is not the minima, right? I don't know why they do that, but you got to actually look at the constraint values as well. But come to step 3. So for an arbitrary point, it will not happen. So you come here. Now you formulate an LP problem. fxt plus del f. So it's a linearized version of the objective function, linearized version of constraints, okay, and the variable bounds. So now you solve this LP. There are lots of softwares to solve LP. I will demonstrate one with the MATLAB later on. Then let's say the solution to this is yt. Okay. Now what you do is join yt with xt you had before, and do a line search along that direction from xt and find the best point. Okay. This is the best point. That's the end of that iteration. At the best point, again you linearize. So it's slightly sophisticated than what I just described before when I said SLP. So here is the whole thing. So let's say this is my feasible region. Somewhere here is the minima. We assume that I know a box that these are my variable bounds, lower bound, upper bound, 2 variable problem. First thing you do is you ignore this circle, right? You are dealing with only the variable bounds here. So let's say this is the optimum. No, this is my initial point. So what I have done is I have linearized this constraint at that point, and you may get a line like this, because linear contours is always a line, right? So I get a line. Along with these 4 lines, I also have a line. So this is my linear programming. And a linear programming problem can always give you one of the extreme points, corner points or something in between. So let's say if I solve this problem, I get that point as my linear solution. So what I do now, I join this with that, and I get a line, and I do a line search. Okay? And let's say this was found to be the optimum. So that's the end of one iteration. Now at that point, I will linearize these constraints again, and I may get this line. So now I had this, now I have that, and now I've got 2 more constraints, rather 1 more constraint, and I solve this problem, and let's say I get that point as my minima. Now I join this with that, and come and minimize, do a line search, and I find this point. Again, I will linearize at that point, continue, and eventually this will take me to wherever the minima is. Okay? So the good thing is every iteration you're solving an LP which has a proof. Okay? But the line search also allows me to get out of the boundaries of the linear region and allows me to go inside. Okay, one other algorithm we're going to talk about is called the feasible direction method. But that is, to me, is one of the most sophisticated methods using point-by-point approach. The algorithms we talked about with the penalty function and the augmented Lagrangian doesn't take advantage of the structure of the constraints, right? It uses the gradients and all that for minimizing, but it doesn't take the constraint structure very well. Now these are more sophisticated than those methods. Okay, so let me first build up the concept of feasible direction. So let's say that I am here at a point xt during the iteration, the whole iteration. I have got a point at certain point that is this xt here, and this is lying on a particular constraint boundary. I don't know where the optima is. So this constraint boundary says this side is feasible. When I put a line like this, it says the opposite side is feasible. Okay, so this is feasible side. All right. Now I'm at this point. So if I draw a derivative of the constraint boundary at this point, it will be this direction, because this is the direction function value is getting increased. The constraint value is getting increased, g value is getting increased, means they are feasible, because I want g to be greater than or equal to 0, right? So if I draw a tangent at this line, any line that is here, okay, so instead of going in this direction, because I know if I go this direction, I'm going to increase my g value, that means I will remain feasible. If I come this way down, my g value drops, and then I might go close, because here my g value is 0, because I am on the constraint boundary, so g value is exactly 0. So if I go up now, if I go up, my function value is, g value is positive. If I go down, my g value is negative. Is that okay? Right? So negative I don't allow, because this is infeasible. Now if I take any direction d like this, if I travel in that direction, do you think my g value is going to be increasing or not? If I go any direction here, like this one here that I'm showing, I don't know why this doesn't come up so quickly. So if I move this direction, is my g value going to, so g value is 0 here, right? If I go this way, my g value is going to increase from 0, because here it is going to increase in a maximum way. That's the direction of the gradient. Any other direction that makes an acute angle with this gradient direction is also going to increase my function value. So any direction you go here from here, you know that you will remain feasible. So that's why if I take a dot product of delta g with the d, and if it's positive or 0 means you will be along these lines, then you remain feasible. So from a current point which you are on a constraint boundary, if you want to remain feasible, all you have to check is in that direction, is this dot product positive or 0 or not? If this is negative, you're going to be violating the constraint. That's of course an approximation of these constraint to linearity. Okay. Now the whole philosophy, this is the philosophy of feasible direction. How do I say, given a direction and given a constraint and a point lies on the constraint boundary, if I go along the direction d, whether I'm going to remain feasible or not? This is the condition to check. Okay. Now let's come back to this algorithms principle, that is the feasible direction method suggested by Zutendijk back in 60s. Let's say I am here at this point which is all on this constraint boundary. Okay, so this thing I wrote here infeasible, but this is the infeasible region. Okay, my dash line is slightly different here, sorry. This should have been here. So this is feasible side. Okay, so this is my del g direction. So any d here, like making an acute angle with delta g, is going to keep me feasible, right? So I can drop a tangent at that point like we have done here, and anything here is going to be feasible. Okay. Now I also have a condition that I not only want to become feasible when I move, I also want to reduce my function value. Okay, what is that condition? That's called the feasibility condition. And that condition is, if I take a dot product of the direction with minus del f is the negative of the gradient. If I take a dot product, then I know the function value is going to drop. If you go this way, if your d is this, is going to drop in a maximum way. But if you go this way, your function value will also drop. So now I have two conditions. One is the feasibility condition to choose a d, and the descent direction, descent condition. Descent means your function value is going to drop. Okay, so when you satisfy those two conditions, so all you're saying now, I'm looking for a d. I'm currently on a constraint surface. I know the constraint surface gradient. At this point, I also know the negative of my objective function minus del f. Now all I am looking for is a d, is a direction to go, which is going to make this condition satisfied, and also the descent condition is satisfied. And the descent condition would be minus del f at the point xt. If I take a dot product with d, that should be positive as well. Or in other words, I can say del f xt dot product d should be less than equal to 0. So that is the condition for descent, d, e, s, c, and d, descent direction. So these two conditions have to be satisfied. If I can find such a d, then I can safely go that way. I know that I remain feasible, and I am also dropping my function value. So in this method, instead of finding a x, they find a direction to go. Okay? How? They solve this LP problem. So you see, now they're saying, is the same sketch I got from the previous slide, is that given the del g, given the minus del f, okay, I am trying to come up with a theta, which is really the value here, because I want this to be as largely negative as possible, because I want it to be negative. So I'm saying theta can be as large as possible, and this theta can be as large positive as possible. Okay, if I can solve this problem, that's why I'm saying maximize theta subject to both the conditions are satisfied. Okay, if I can find that, then you found a d. Most likely it's going to be intermediate. It's going through intermediate through that. If there are many constraints, you have to just add for each of those active constraints, a similar constraint will come here. But fortunately, this is an LP. You can solve the LP calling a software. All you find is a d. And then the algorithm goes into the loop. Okay. So I'm not talking about the rest of the algorithm, but I'll just quickly go through it just to show without showing you any details. So here is my feasible region for the problem, one constraint and another constraint here. And my optimum is this, because optimum is to find the distance from this point to any point on the feasible region. So I'm starting with this, where I have got two constraints. One constraint is this, another constraint is that. So the grad g1 is this one for that constraint, and grad g2 is that one for this constraint, and minus grad f is this. So when I solve the LP, I actually find this as my direction. See, it makes a nice compromise between minus grad f and grad g1. Okay, so this is the direction. Then what the algorithm does is it goes and finds how much can I go along that direction before I become infeasible. So that becomes its lower bound and upper bound, and it does a line search, and it finds the best point. Now this is your end of one iteration, and now you get into a situation where this new point is not on any constraint boundary. That means you are in the interior of the search space. When you're interior in the search space, the best thing you could do, okay, so if you're interior in the search space, what is the best direction? Let me ask this question now. So when you are on the constraint boundary, okay, you cannot go in all directions, because constraint says certain directions only you can go, and that's given by these feasibility direction condition, right? But now if I'm interior, like here, no constraint is close to me, what is the best direction to go? Negative of the gradient. So this algorithm defaults into that steepest descent. So at this point it finds the negative of the gradient, and this is that direction, and it goes and finds the optima. Okay, so all these are actually talking about this. I'm going to skip the gradient projection. This is again another extension of this. When for equality constraint this algorithm is used, it always traverses through the constraint boundary. So I'm not keeping this into this course, okay, but it's just there. Okay, so I think I'm almost end of this morning class, so I have to do this for tomorrow, the linear programming. So we'll start from here. Again, you said that a couple of people have done linear, few of you have done linear programming before, right? So I will assume that the whole class doesn't know, and just give you an introduction to LP in the next class. But is there any question? So what I've done now is that today we've covered the algorithms for multivariable. There are a few that were left, and then the constraint optimization theory, and few constraint algorithms, okay, that are popularly used. There are actually hundreds of algorithms for doing constraint optimization, but there are many sophisticated methods that actually are coded in algorithms like softwares like MATLAB and KNitro, and there are various methods. But I'm giving you some very basic algorithms and their principles. One thing you get from all these is they're very detailed. They use gradient information quite well, the structure of the constraint. They are involved. So in practice, you may be using a software eventually, but this kind of exposure gives you an idea what goes inside the software. They are never so simple in nonlinear optimization. They are iterative. There are a lot of checks and balances that you go. So that's full of these. So when you talk about linear programming, quadratic programming next, these are very structured only to be able to solve certain class of problems. But now you see that when you're talking about a nonlinear programming algorithm, like feasible direction, it calls linear programming. When you're talking about ALM, it calls the steepest descent. So it's always like that. One algorithm is built up on something simpler because you know how to do the simpler one. Now you're trying to graduate to solving a more complex problem. So you borrow the idea from simple cases. So this is how the whole thing goes, okay? All right, so what we'll do at 2 o'clock is we'll have, for about 40 minutes, we'll have the assignment problem solving, and then we'll have the quiz. Quiz will take about 40-45 minutes, okay? So we will start the third one, exercise 3 on page 171. I don't think we'll be able to solve all of them. So I'll say that we'll do the problem 1. That's it. We'll just do problem 1. I think it's going to take us at least half an hour to 40 minutes. Okay? And then, because I have not done the linear programming yet, so it's no point. I cannot give you that assignment anyway. Okay? And then we'll move to the quiz. So if you want to prepare a little bit, the quiz would be everything that we have done, let's say, till last class. Okay? I'm not including what we have done today. So the first 2 classes and the tutorials, all inclusive. Any question? Oh, assignment you have to submit. They have already submitted? Okay. Okay. You want to do every day that way? Okay. We'll have to see at the end, the very last assignment, what to do. Okay, we'll see. Last one you will only do that day. Okay, we'll see. We'll see. Okay, if that suits you, it's fine with me. We will also be grading them and giving you back. So we will see how soon they will grade, and then because there are quite a few here, so we'll not be able to do it in one day, I suppose. But you will get back. You'll get back your graded assignments. Okay. Any question about the exam, about the quiz, or anything? Yeah. So revise the tutorials, the exercise problems you have done yesterday, and the first day, and the material that we covered the first 2 days. Okay. All right then. See you later.